This is lecture 3 of our class, and we are going to talk today about node embeddings. So the way we think of this is the following. What we talked on last week was about traditional machine learning in graphs, where the idea was that given an input graph, we are going to extract some node, link, or graph level features that basically describe the topological structure of the network, either around the node, around a particular link, or the entire graph. And then we can take that topological information, combine it with the attribute-based information to then train a classical machine learning model like a support vector machine or a logistic regression to be able to make predictions. So in this sense, right, the way we are thinking of this is that we are given an input graph here. We are then creating structured features or structural features of this graph so that then we can apply our learning algorithm and make prediction. And generally, most of the effort goes here into the feature engineering, where, you know, we as engineers, human scientists, we are trying to figure out how to best describe this particular network so that it will be most useful for downstream prediction task. The question then becomes, can we do this automatically? Can we kind of get away from feature engineering? So the idea behind graph representation learning is that we want to alleviate this need to do manual feature engineering every single time, every time for every different task. And we want to kind of automatically learn the features, the structure of the network that we are interested in. And this is what is called representation learning, so that no manual feature engineering is necessary anymore. So the idea will be to do efficient, task-independent feature learning for machine learning with graphs. The idea is that, for example, if we are doing this at the level of individual nodes, that for every node, we want to learn how to map this node in a d-dimensional space and represent it as a vector of d numbers. And we will call this vector of d numbers as feature representation, or we will call it an embedding. And the goal will be that this mapping it happens automatically, and that this vector captures the structure of the underlying network that we are interested in analyzing or making predictions over. So why would you want to do this? Why create these embeddings? Right? The task is to map nodes into an embedding space. And the idea is that similarity of the embeddings between nodes indicates their similarity in the network. For example, you know, if both nodes are close to each other in the network, perhaps they should be embedded close together in the embedding space. And the goal of this is that kind of automatically encodes the network structure information. And then, you know, it can be used for many kinds of different downstream prediction tasks. For example, you can do any kind of node classification, link prediction, graph classification, you can do anomaly detection, you can do clustering, a lot of different things. So, to give you an example, here is a plot from a paper that came up with this idea back in 2014, 2015. The method is called DeepWalk. And they take this small network that you see here, and then they show how the embedding of nodes would look like in 2 dimensions. And here the nodes are colored by different colors. They have different numbers. And here in this example, you can also see how different nodes get mapped into different parts of the embedding space. For example, all these light blue nodes end up here. The violet nodes from this part of the network end up here. You know, the green nodes are here. The bottom 2 nodes here get kind of set on a different in a different place. And basically what you see is that in some sense, this visualization of the network and the underlying embedding correspond to each other quite well in 2-dimensional space. And of course, this is a small network. It's a small kind of toy network, but you can get an idea about how this would look like in more interesting, larger dimensions. So that's basically the idea. So what I want to now do is to tell you about how do we formulate this as a task, how do we view it in this encoder-decoder view or definition, and then what kind of practical methods exist there for us to be able to do this. So the way we are going to do this is that we are going to represent a graph with an adjacency matrix. And we are going to think of this in terms of its adjacency matrix, and we are not going to assume any features or attributes on the nodes of the network. So we are just going to think of this as a set of as an adjacency matrix that we wanna analyze. We are going to have a graph, as I show it here, and the corresponding adjacency matrix A, and for simplicity we are going to think of this as undirected graphs. So the goal is to encode nodes so that similarity in the embedding space, similarity in the embedding space, you can think of it as distance or as a dot product, as an inner product of the coordinates of two nodes, approximates the similarity in the graph space, right? So the idea will be that in the original network, I want to take the nodes, I want to map them into the embedding space. I'm going to use the letter Z to denote the coordinates of that embedding of a given node. And the idea is that, you know, some notion of similarity here corresponds to some notion of similarity in the embedding space. And the goal is to learn this encoder that encodes the original network as a set of node embeddings. So the goal is to define the similarity in the original network and to map nodes into the coordinates in the embedding space such that similarity of their embeddings corresponds to their similarity in the network. And as a similarity metric in the embedding space, people usually select dot product, and dot product is simply the angle between the two vectors, right? So when you do the dot product, it's the cosine of the angle. So if the two points are close together or in the same direction from the origin, they have high dot product, and if they are orthogonal, so there is kind of a 90-degree angle, then they are as dissimilar as possible because the dot product will be 0. So that's the idea. So now what we need to define is we need to define this notion of similarity in the original network, and we need to define then an objective function that will connect this similarity with the embeddings. And this is really what we are going to do in this lecture. So to summarize a bit, right, encoder maps nodes to embeddings. We need to define a node similarity function, a measure of similarity in the original network, and then the decoder, right, maps from the embeddings to the similarity score. And then we can optimize the parameters such that the decoded similarity corresponds as closely as possible to the underlying definition of the network similarity, where here we are using a very simple decoder, as I said, just the dot product. So encoder will map nodes into low-dimensional vectors. So encoder of a given node will simply be the coordinates or the embedding of that node. We talked about how we are going to define the similarity in the embedding space in terms of the decoder, in terms of the dot product. And as I said, the embeddings will be in some d-dimensional space. You can think of d, you know, between, let's say, 64 up to about 1000. This is usually how many dimensions people choose, but of course it depends a bit on the size of the network and other factors as well. And then, as I said, the similarity function specifies how the relationship in the vector space map to the relationship in the original network, and this is what I'm trying to show an example of here. So the simplest encoding approach is that an encoder is just an embedding lookup. So what do I mean by this? Is that an encoding of a given node is simply a vector of numbers, and this is just a lookup in some big matrix. So what I mean by this is that our goal will be to learn this matrix Z, whose dimensionality is D, the embedding dimension times the number of nodes in the network. So this means that for every node we will have a column that is reserved to store the embedding for that node, and this is what we are going to learn, this is what we are going to estimate. And then in this kind of notation you can think of V simply as an indicator vector that has all zeros except a value of 1 in the column indicating the ID of that node V. And what this will do pictorially is that basically you can think of Z as this matrix that has one column per node, and the column a given column stores the embedding of that given node. So the size of this matrix will be number of nodes times the embedding dimension. And people now who are, for example, thinking about large graphs may already have a question, won't this be a lot of parameters to estimate? Because the number of parameters in this model is basically the number of entries of this matrix, and this matrix gets very large because the size of the matrix depends on the number of nodes in the network. So if you want to do a network over, I don't know, 1 billion nodes, then the dimensionality of this matrix will be 1 billion times, let's say, 1000 embedding dimension, and that's a lot of parameters. So these methods won't necessarily be most scalable. You can scale them, let's say, up to millions or a million nodes or something like that if you really try, but they will be slow because for every node we essentially have to estimate the parameters. Basically, for every node we have to estimate its embedding vector, which is described by the d numbers, d parameters, d coordinates that we have to estimate. So, but this means that once we have estimated these embeddings, getting them is very easy. It's just a lookup in this matrix where everything is stored. So this means, as I said, each node is assigned a unique embedding vector, and the goal of our methods will be to directly optimize or learn the embedding of each node separately in some sense. And this means that there are many methods that will allow us to do this. In particular, we are going to look at two methods. One is called deepwalk, and the other one is called node2vec. So let me summarize. In this view, we talked about an encoder-decoder framework, where we have what we call a shallow encoder because it's just an embedding lookup. The parameters to optimize are very simple. It is just this embedding matrix Z, and for every node we want to identify the embedding Z sub U. And what we are going to cover in the future lectures is we are going to cover deep encoders like graph neural networks that are a very different approach to computing node embeddings. In terms of a decoder for us will be something very simple. It will be simply based on the node similarity based on the dot product. And our objective function that we are going to try to learn is to maximize the dot product of node pairs that are similar according to our node similarity function. So then the question is, how do we define the similarity, right? I've been talking about it, but I've never really defined it. And really, this is how these methods are going to differ between each other, is how do they define the node similarity notion? And you could ask a lot of different ways how to do this, right? You could say, should two nodes have similar embedding if they are perhaps linked by an edge? Perhaps they share many neighbors in common, perhaps they have something else in common, or they are in similar part of the network, or the structure of the network around them looks similar. And the idea that started all this area of learning node embeddings was that we are going to define a similarity of nodes based on random walks, and we are going to optimize node embeddings for this random walk similarity measure. So let me explain what I mean by that. So it is important to know that this method is what is called unsupervised or self-supervised, in a way that when we are learning the node embeddings, we are not utilizing any node labels. We'll only be basically trying to learn embeddings so that they capture some notion of network similarity, but they don't need to capture the notion of labels of the nodes. And we are also not utilizing any node features or node attributes, in a sense that if nodes are humans, perhaps their interests, location, gender, age would be attached to the node. So we are not using any data, any information attached to every node or attached to every link. And the goal here is to directly estimate a set of coordinates of a node so that some aspect of the network structure is preserved. And in this sense, these embeddings will be task independent because they are not trained on a given prediction task, a given specific labelings of the nodes, or a given specific subset of links. It is trained just given the network itself.